Welcome, grade 12s. Can you believe it's June already? Well, almost June, and it's time to prepare for our June exams. And what we're going to do today is we're going to do some preparation for your June exams, but please remember, grade 11s, that your own teachers, if you're writing internal exams, may choose to put grade 11 work into your June exams, or if you're writing the external, there may be grade 11 work in there. So please make sure you check and make sure you know what your June exam is going to be on besides just the grade 12 work, okay? So that's really important. Now, obviously, we can't revise absolutely everything we've done, and the way today is going to work is we're going to do some problems and we're going to see how much we get through, okay? And what we're actually going to focus on is we're going to do vertical projectile motion, we're going to look at momentum, and we're going to look at work, energy, and power. Now, I'm going from the point of view that you've done some studying, hopefully, done a little bit of revision, and you're going to be okay with these, all right? So let's just get stuck in there, and we're going to go bit by bit. We'll see how far we get. First one is, here's a question which we've adapted from a prelim paper from last year from the Metro South, that's in the Western Cape. The position time graph is given for a ball which is thrown, so that actually should be over here. Oops, no, over here. Sorry, that's just a bit of a typo. My fault. Is thrown down from a vertical height of 1,8 meters and bounces once on reaching the ground. Contact time between the ball and the floor can be ignored. So there's the position time graph. It's a really easy one. So they show you, the nice thing is they've given you the position. So what we're going to do is, here's the first question. And that first question is, calculate the initial velocity with which the ball was thrown. So I'm going to give you 1 minute. Okay, we're going to go quickly today. So I'm going to give you 1 minute. Using the graph, I want you to calculate the initial velocity at which the ball was thrown. And your 1 minute starts now. Okay, let's see how you did, grade 12. So they wanted initial velocities. Now, when you look at your information, what you need to recognize here is that they told you that it's thrown down. So initial velocity cannot be zero, and that's what we were asked to find. This value is going to give me displacement, and that value is going to give me time. So what we need to also recognize is that it's going to be vertical motion. So we always write a list because a list makes our lives so much easier. Okay, now when we look at this list, we go, well, we don't know the final velocity, we actually can't work it out. Initial velocity is what I'm looking for. Now we need to make a decision because it's a vector question and we need to decide which direction is positive. So now look at what they've got over here, okay, is it's thrown to the ground, and on reaching the ground, the contact time between the ball and the floor can be ignored. What you need to recognize is, if this is my starting point, okay, down is my positive direction. Okay, I'm taking down as my positive direction. That's quite important. Okay, so I'm taking down as my positive direction. That means my acceleration is 9,8 meters per second squared. That never changes. The time was 0,5 seconds and it was 1,8 meters. So now we look at the information and we want VI. We go onto our information sheet and we look at the equations that are given and we decide then which one is most useful. Anyone with VF is just useless to us because we don't know VF. So the one we're actually going to use is delta Y equals VI delta T plus a half A delta T squared. Now, grade 12s, please, it must be delta Y, not delta X, otherwise you're not going to get any marks. It's going in the vertical direction. So VI is what I'm looking for. Delta Y is 1,8. VI I'm looking for. that was 0.5. This is a half. 9.8 times 0.5 squared. Guys, just because of time today, I'm not going to do all the maths. Hopefully you guys can work that out. And VI is 1.15 meters per second. First question, done. We're happy. So now let's look at the second question. Okay, we're sticking with the same graph, so the ball hasn't changed. But now what I'm going to ask you to do is I want to know at what speed does the ball strike the ground. So now we're looking for VF. Okay, and what I want you to do here is stick with the initial velocity that I worked out now for you, so we don't have any carry on down errors. Okay, so your graph, you know what it looks like. This is what the graph looks like. None of the information has changed, so you're going to use the same information. And now what I need you to do is I need you to calculate the velocity at which it strikes the ground, and you have 1 minute starting from now. So let's see how you did. Now there's more than one way to do this. The easiest way to do this question is actually to use VF equals VI plus A delta T. Okay, because I know VI is 1.15, I know A is 9.8, that hasn't changed, and the time it takes is 0.5 seconds. We plug that into our calculator and we get that it hits the ground at 6.05 meters per second, okay? So now I know initial velocity, I know final velocity. So if we go back to our graph, all right, so over here, I know that my initial velocity, over here, we know that VI at this point was 1.15, and I know now when it hits the ground over here, that the final velocity over here was 6.05, okay? Now, when we go to the next question, all of it just follows on from what we're doing, okay, don't stress. Now they say to us, at what speed did the ball leave the ground after bouncing? So now we go back to the graph, and I've got a clean graph because I want you to see something here. They're now asking, we know the velocity when it comes down. They want to know what's the velocity when it goes back up. Okay, now we've taken down as positive. That can't change. We're now changing the part of the motion that we're looking at. So now we've got to consider that part. Okay, the height is now 0.9. I know final velocity, when it gets to the top of the motion, remember final velocity is 0. So using that information, I now want you to calculate what the velocity is when it leaves the ground again. And once again, you have 1 minute, and that minute starts now. Okay, so let's see how you're doing. All right, we wanted VI. We know VF is 0. We know A is 9,8. It's still down. Delta T we don't know. Delta Y is the important one here. Delta Y is above where it started on the graph. So it's negative 0,9, not positive. Otherwise, you're going to run into trouble here. So now VF squared, this is the best equation to use because it doesn't require me to know time. If I want to use the ones with time, then I'm going to have to work it out first, and that one in this equation is going to actually get quite, it's going to get a bit hairy, so let's not do that one, okay? VF is 0, okay? VI is what I'm looking for. We know this is 9,8, and here, with this particular equation, you're going to know if you've made a mistake, because if you don't, which is what I was about to do here, is if you don't put in the negative by that 0,9, when you take that over, you're going to end up having a negative number that you need to square root, which of course you know you can't do, all right, because you're going to go 2 times 9,8 times negative 0,9, take it over, it becomes positive, and when you square root it again, you get 4,2 meters per second, okay, and of course it's going up. All right, sticking with the same graph, we're not changing anything. Now they want the value of time, so of the t, of this time here. Okay, they want the value, let's see again, of time t. So we go here, and what they want is they want to know what is that value, okay? I'm not going to give you any hints on this one. You have a minute, and it starts now. Time's up. Let's see how you did. Now what's really important, there's lots of ways you can do this one, grade 12s, but when you look at the mark allocation, it's only worth 4 marks. That means you shouldn't be doing lots and lots of equations. What actually can happen here is you can consider this whole part of the graph, this part, as one motion. We know that it's leaving the ground at, what was it, 4,2 meters per second. That means that it's going to hit the ground again at 4,2. All right, that is the point here. So when we look at this one and you go, well, if my initial velocity is up, that makes it minus 4,2. My final velocity when it hits the ground is going to be positive 4,2. A is positive 9,8. And now I'm going to work out delta t. So if I go VF equals VI plus A delta t, then VF is 4,2, VI is minus 4,2, this is 9,8, we want delta t, so we're going to end up with 8,4 divided by 9,8, and delta t is 0,86, but that's not my final answer because that is only the time it takes to go from 0,5 to t. So if I want the total time now, so this is 0,86, if I want the total time, I need to add that together. So to get the time at t, it's going to be 0,5 plus the 0,86, okay, and we put that into our calculators and we get 1,36 seconds, all right? Last question, which actually I'm going to do with you because it's going to be easier. Now, what they want us to do is to sketch a velocity time graph to represent the motion of the ball. Indicate the following values on the graph. So now, Let's write these in as we read it. So it says the initial velocity at which the ball was thrown. That was 1,15 meters per second, and that was positive. The velocity at which it strikes the ground, and that value was minus 4,2. The velocity at which it bounced off the ground was, no, that's the velocity which it bounced off the ground. It struck the ground. Oh, let me go back here. Now I'm lying to you, see? It's very important that I'm hoping somebody's screaming at the TV right now. Just be quiet. Don't make it too loud. It strikes the ground at 6,05. That's right. Then it bounces back up at minus 4,2. The time at which it strikes the ground for the first time, that's 0,5 seconds. The time t that it strikes the ground again, which is 1,36 seconds. Okay, so on our graph, we know that we've got to start with the initial, which is 1,15, so I'm going to put that here, 1,15. Then we know it goes to 6,05. So it was thrown down and it goes higher. So it must end over here at 6,05. Then it strikes the ground. At that point, we draw our line going all the way down. Okay, now it changes velocity and it bounces off the ground at minus 4,2. And remember, it strikes the ground here at 0,5. Then it's going to go back. It's going to go through 0, and then it's going to hit the ground again. Okay, and remember, this would be at 4,2, so it's probably going to have to be up there somewhere. And this time is 1,36 seconds. So what are we looking for? Your axes, labeled units, all the rest of it. 2, that you have 2 parallel lines, okay, same gradient, mine are slightly off, but you make sure it's the same gradient. And then 3, they're looking for these. So they're looking for 1, 2, and then you've got your 3, and then your time is 4. They're looking for all the values that you found. Obviously, if the values that you found in the question are wrong, then they will carry those values into your graph. Okay. So lots of stuff. Sure, your brains are hurting a little bit, but we're going to take a little break, and when we come back, we're going to look at momentum. So I'll see you in a couple. Okay, let's tackle momentum. Okay, in fact, this is such a nice question. It's from the Eastern Cape prelim paper from last year. And it says to us, a boy on a skateboard moves at 5 meters per second to the right towards point A. Okay, and they give you a nice diagram at the bottom of a slope, which is 1,6 meters high, given he's carrying a 4-kilogram parcel, so let's write that in. The total mass of the boy, his skateboard, and the parcel is 70 kilograms. So my total mass is 70 kilograms, so let's write that in. He needs to increase his speed in order to reach point B at the top of the slope. He decides that if he throws the parcel horizontally, it will increase his forward velocity. Grade 12s, you have to get over the fact that this may or may not work in real life. You have to get over the fact that to throw perfectly horizontally probably won't happen. It doesn't matter. Just take the question at face value. And I'm probably speaking specifically to the boys who tend to overthink these questions. Okay, oh, but it doesn't work. Pretend it's a movie, and of course, you know everything works in movies, okay? It doesn't matter if it obeys the laws of physics or not, because they'll make it work, because it's amazing what we can do in movies. So, that's the situation, okay? Now, the first 3 questions are all theory-type questions. So, there's my situation. Here are my 3 questions. I want to know which direction must you throw it. I want to know which law we're using, and I need you to state the principle of conservation of energy. Okay? So, 3 questions, 1 minute, off you go. Right, so let's see how you did. Okay, so first of all, in which direction must he throw the parcel in order to increase his forward velocity? Now, he wants to go to the right, which means he needs to throw the parcel to the left. Okay, and in figuring that out, we're actually using the law straight away. It's not Newton's first law, so it's not got nothing to do with inertia. It's not Newton's second law. This is a Newton's third law question. That's what makes this such a nice question, okay? So here, we have to throw it to the left, so that's what we write in. Now, we've just said which law were we using? Well, we're using Newton's third law of motion. Guys, please, 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 don't just say third law. Name it properly. It is Newton's third law of motion. Okay, don't get lazy. You have time in the exam. Then it seems like a random question. They ask you to state the principle of conservation of mechanical energy. This is actually quite an important question because it leads you into the next part of this. Okay, so that's why it's here. So it says state the principle of conservation of mechanical energy. Well, there's a couple of important things. In an isolated system. Isolated, closed system. Okay? Mechanical energy is conserved. Okay? Oh, sorry, total mechanical energy. Let's put that in there. Total mechanical energy is conserved. I have to be honest, I have a bit of a problem with that definition because I'm using the word conserved in it, but it doesn't matter. What that means is it remains constant. Okay? Remains constant. Nice and easy. So, let's see what the next question is. Now I'm going to give you some time to do it. Now it says, calculate the velocity of the boy immediately after the parcel leaves his hand in order for him to reach the top of the slope at point B. Okay, so we go back here. I want to know what is his velocity here? Okay, what's that velocity if he's going to get to point B? Okay, you can assume that when he gets to point B, that his velocity over here is 0. It's the only way you can do this one, okay? So now I'm going to have to give you a little bit more time because this one is going to take you longer to work it out. So I'm going to give you 2 minutes and you now need to work out what its velocity needs to be. So your 2 minutes starts now. Okay, I'm pretty sure you're not done yet, but it's all right. We need to carry on. Now, This is why they asked you 2.3, because in order to know if it's going to get to the top of the slope, I need to remember that the mechanical energy at point A will be equal to the mechanical energy at point B. And remember, your mechanical energy is your potential energy at A plus the kinetic energy at A, which is going to be equal to the potential at B plus the kinetic at B. So when we go back to A, we go, well, at point A, we look at point A and we go, well, the height is 0, and we're actually looking for the velocity. So when I come back here, I can say 0 for the potential, not going anywhere, half m, oh, no, I'm lying, let's take that back. Now, the mass here is quite important, because the mass of the boy plus the skateboard plus the parcel was 70 kilograms. The total mass was 70 kilograms. Here, I'm only considering the boy and the skateboard. If the parcel has a mass of 4, then the mass that I'm looking for here is 66 kilograms. That was a bit of a trick on this one. Okay, so this is 66, or not, depends on whether I make it so that you can read it. I'm suspecting, should I speak English for you, that reading it's a good idea. Oh, and that should be v squared. I'm sure somebody noticed that. So there's the velocity that I want. When it gets to the other side, it's going to have that, and the height, if we go back here, as we say, well, the height that it needed to get up to was 1,6 meters. Okay, and the velocity, assuming that it gets to the top, is 0, so then it's 0 kinetic energy. And actually, if you look at this, this is now simply a maths problem. Okay, and what you end up with is that your VA, your velocity at A, is 5,6 meters per second. Now, if you got an answer here less than 5, you've definitely made a mistake, because wasn't the point of him throwing the parcel to make him go faster? And he wanted to go faster so he could get up the hill. Needs to be bigger than 5, okay? So, and I know some of you are going, where's the momentum question, Tracy? It's coming up right now. So, the velocity over here after he's thrown the parcel is 5,6. Now they ask you, calculate the minimum velocity with which he must throw the parcel in order for him to reach the top of the slope. In other words, this is momentum. So you look at this and you go, one object before, boy and parcel, 2 objects afterwards. We want to know what velocity the parcel needs to be thrown at in order for the boy to have a velocity of 5,6. And together they start off at 5. Okay? So I'm going to give you 2 minutes again, because this one's a little more difficult again. All right, so I'm giving you 2 minutes to tell me what velocity the parcel has to be thrown at, and your time starts now. So, grade 12, let's see how you did. This question is a momentum question. One object became two. So that means we have to start with the fact that we're going to use the sum of the momentum initially, okay, is equal to the sum. Well, that is not even vaguely a sum sign. That doesn't even look like a sigma. So let's do that. Is equal to the sum of the momentum final. Okay, now before they were one object, so we can take the total mass with their initial velocity. They were one object. Afterwards, we have the mass of the parcel with the parcel's final velocity plus the mass of the boy and his final velocity. Now, what I haven't done here is I haven't chosen a direction as positive, and I'm going to take to the right as positive, just because I know I've got two velocities to the right to start off with, so it's going to make my life a bit easier. Now, the boy was 70 kilograms and with the skateboard and the parcel, and they were going at 5. Afterwards, the parcel, which has a mass of 4, has a velocity which we are looking for. The boy has a mass of 66, and we know that it's going at 5.6 meters per second. Now, all we have to do is solve for VP, which I've done, and what we get, now watch here, is you get a negative answer. That negative answer is really important because that negative answer tells me, which is what we expected, that we need to be able to do it to the left. Okay, very, very important, and that's what we said at the beginning. Okay, now, I'm going to do this one with you because this is quite an important question. It says, how will the answer in question 2.4, in other words, the velocity we have him moving at, be affected if the boy throws the same parcel with a higher velocity in the same direction? And then they say, right, increase, decrease, remains the same. So what you need to recognize here is your change in momentum must remain constant. Your total change in momentum, okay? So because we're going in opposite directions, what's going to happen here is if the change in momentum for the parcel increases, and I'm going to put an up arrow for this, okay, increases, the change in momentum for the boy must also increase, because they're going in opposite directions, and together they must still give us the same total momentum, okay? So their momentum before and after, if the parcel's momentum afterwards is going to increase, the boys must increase as well, because when I minus them from each other, they must give me the same original total. But what's very important here is this is if, so for, now this is the important part. So for the same mass of the boy, this is really important. That's got to stay the same. Your velocity increases, okay? And I think the pen doesn't like me anymore. So our answer increases, okay? Increases, very important. Our brains are hurting even more than it did just now. That's all right. So grade 12s, take a little break, and when we come back, we'll look at some work energy and power. Okay, you ready to tackle work energy and power? Of course we are. Don't groan, it's not so bad. This is practice, practice, practice. So, once again, a prelim paper. This is from 2014 from the Free State. It's a nice question. It says to us, a 3-kilogram metal block moves from rest at point A, and I'm tired of the pink, so I'm going to change colors to this. So my initial velocity is 0. Down an inclined plane as shown in the diagram, reaches a speed of 6. So over here we have 6 meters per second, so I'm going to write that in. The section from A to B is frictionless. We like that, okay? And they don't give me any more information there. So, first question says to us, would you describe the movement of the block on section A, B of the path as free fall? And then give a reason for your answer. I need you to think about that, so I'm going to give you a minute, and your minute starts now. Okay, so grade 12s. They said, would you describe the movement of the block on section A of the path as free fall and then give a reason for your answer? I'm pretty sure, and we're not going to ask for hands because I can't see them anyway, that a lot of you said no. And your reason for that is going to be, well, it's on a slope. It's falling on something. This is where we're testing your definition of free fall. Free fall is defined as the motion of an object is in free fall when it is only acting under the force of gravity. Now, because they told me the slope was frictionless between A and B, it is absolutely in free fall. So the answer here is yes, only gravity acts on the object. X. There we go. All right. So that's really important. Free fall is that only gravity acts on the object. Okay. So now it says calculate the net work done on the block as it moves from section A down section A, B of the path. So just to remind you, initial velocity here is 0. Velocity over here is 6. Okay, at B, and they want to know, so now I want you to calculate what the net work is between A and B, and you're going to need 2 minutes to do this, so your 2 minutes starts now. Okay, so let's see how you're done. This is such a nice question because it really does test work energy theorem. Net work done, and this is why they asked, is equal to change in kinetic energy. There's no other way you can do this. You cannot use forces, okay? So that means we have to take the velocity, the kinetic energy at B, okay? Let's just make that we'll make that a B rather. So we're going to take the kinetic energy when it gets to B and minus the kinetic energy from A because that was the initial and it's always final minus initial, and we know they told me that the object was 3 kilograms, this was 6, and that's 0 because it wasn't moving, so net work done is 54 joules. Okay, now the next question I'm actually just going to do with you because we've done one like this, because what they now ask you to do is to calculate the height of the block at position B. And because it's height, we know initial velocity, final velocity, and we know over here, if you look here, all right, so this one is, we already know what that height is, okay? So we want to know what the height at point B is. We know velocity, so we're going to use the same concept we used in the last question, in that we're going to say the mechanical energy at A is equal to the mechanical energy at B. Okay, and I'm doing this because I want you to work on another one in a second. So the potential at A plus the kinetic at A is equal to the potential at B plus the kinetic at B. And what I know at A is that this is 3, that's 9,8, and we look at our diagram again, and it was 6 meters above the ground. So we're going to put in the 6. We know that it's not moving, so kinetic energy is 0. Okay, we know that this is 3, we know this is 9,8, we want the height at B, and of course, we know how fast it's going at B. Once again, it's a maths problem, okay? We don't have time for me to show you that, unfortunately, but the height at B is 4,16 meters, okay? So we go back here, and we know, so V here is 0, that's 6 meters per second, and the distance to get to B over here is 4,16 meters. Now they say to us, same thing, but now they say to us, on reaching B, the block continues to move down section BC, which is 5 meters in length. So this part here is 5 meters, okay? Then they say to us, the block now experiences a frictional force and reaches C at 2 meters per second. Now it says, using the principle of conservation of energy, calculate the magnitude of the frictional force acting on the block as it moves down BC. I can hear the groans, can you? All right, you have 2 minutes and your time starts now. Grade 12s, how many of you got 28,18 newtons? Oh, I can hear the screams. Don't tear your hair out. With something like this, as soon as we have friction, we can't use mechanical energy at B and C. Okay, what we have to use is work done by the non-conservative force, which is your change in EK plus your change in potential. Your non-conservative force is friction. So that means I've got to do friction, delta x cos theta, okay, is going to be the kinetic energy at C minus the kinetic energy at B plus the height at B minus the potential at B. This is why you had to work out the height. So, and I'm going to have to go very quickly because we want F, X is 5, it's friction, so it's cos 180, and we have a half times 3 times 2, because I know how fast it was going at C, minus a half times 3 times 6, because I know how fast it was going at B, plus, okay, and the height at, it's still 3 kilograms, sorry, that's 9,8. The height at C was 1 meter, minus, say bye-bye. Ooh, I am just making big messes. There we go. So what happens when you try to work fast? It's minus, and that's 3, that's 9,8. You worked out the height is 4,16. Maths problem. Yeah, and you can work that out, and your friction is 28,18 newtons, okay? And you must get a negative answer for this part, okay? Because you're going to divide by cos 180, which is -1. Very, very, very important. This was the hard part. The rest is maths, okay? Grade 12, the only way this gets easier is by practice, practice, practice. Exam time, practice, okay? Study hard. Make sure you know your definitions. Make sure you know how to use your information sheet. And the more questions you do, the better you will get at them, because you'll notice that we can only ask things so many ways. So get your hands on every single possible question you can, okay? Practice, practice, practice. Use your time effectively. Next time, we're going to look at some chemistry, okay? And some of you are going, yay, some of you are going, Anyway, I'll see you next time.